So many of us at IIA Kolkata. His hobby is practicing karate, so we practice.
Yeah. Start. Okay. Thank you, Sakshi, for brief introduction. Any mistake? I am not yet doctor. I am only Mr. yet. I had not defended my thesis. Anyway, thanks Dibyendu for inviting me here. Although I miss him. Anyway, that's unfortunate. So okay. So this is the talk title I will discuss. So as Dibyendu asked me, I will discuss basic ideas of exoplanetary atmosphere modeling from a theoretical viewpoint. From the theoretical viewpoints, okay, so today I will discuss ready? So today I will discuss about modeling of exoplanetary atmosphere, a brief theoretical idea. This is the main focus of my PhD work, which I have done from Indian Institute of Astrophysics with Professor Sujan Sengupta. So I will discuss the basic things as well as Dibyendu requested, I share some of my PhD stories so that it might be helpful for PhD students here. So this is the brief outline of my today's talk. At first, I will go through introduction of exoplanets. Then I will discuss one idea that how from just simple observation of a very distant planets, almost about parsecs, can we say that is there any atmospheric flow or not? So this will be my first topic of discussion. Then I will discuss something known as modified theory of Chandrasekhar's diffuse reflection problem. This is an indigenous problem handled by us, and we got some good results. And I'll end up with. So let's start with introduction. So as far as you know, there are more than 5,000 discovered till now, starting from 1995. Uh, I have enlisted some of the very interesting exoplanets like terrestrial hot Jupiter, sub-Neptunes, and diamond planets. There are plenty of other exoplanets. I named some few. My main interest is about hot Jupiter exoplanets only, this kind of things. So let's talk about more on hot Jupiter. This is the TOI-1. This is one particular hot Jupiter which is very near to its host star. But there is an interesting story. This is only one exoplanet discovered from Indian scientists, like a team led by Abhijit Chakravarti in PRL. And this discovery was done by one of his PhD student, Akanksha. It's very exciting. Till now, we have only one exoplanet discovered from India, like our own exoplanet, you can say. And this. So anyway, so hot Jupiter has a distance from its star of about 0.05 AU. This is much less than our own Mercury. That is, this planet is very much close to its host star. Okay, and the second thing is Jupiters are gas giants. Like till now, there are no evidence that Jupiter has a rocky surface. That means if you jump on a Jupiter surface, you will falling towards the center, and you will not leave until you reach the center. So it's so hot. Okay. So what are the basic properties of Jupiters? They are gravitationally locked to. So what does it mean by gravitational lock? Okay, so I want this interactive session. So if anyone have any doubts, just stop me and ask questions. Okay. So what does it gravitationally locked means? So a famous example is Earth and Moon system. Why? Because we always see one surface of the Moon, and is simply Moon's rotation period is simply same with its orbital period. That means Moon's one surface is always face to the Earth and other surface is fully dark. Same thing goes for this type of hot Jupiters. One surface of these Jupiters always face the Earth and other surface is always a permanent night, you can see. So what does it mean? At the day side, there is very high irradiation from its host star, and at the night side, no irradiation comes at all. So there is a huge day to night temperature contrast. Can you guess? It's almost 1500 to 2000 Kelvin if you go from one hemisphere to the other hemisphere. Okay, so this will uh, give us the idea why we discuss about our first project in a little after. These are some detection techniques. This was published by NASA on 17th November 2023. There are many different techniques to detect exoplanets like radial velocity, transit, microlensing, and all. I am mainly focused on transit light curve method. Why? Because you can see, depending on the periods, if the periods are less, close to their host star. Why? Kepler's law. Second thing, the detected planets are about Jupiter's mass. So this green region mostly consists of hot Jupiters, and all these green planets the transit method. So my work is mostly focused on modeling the planets for transit, which can be detected using transit light curve method. Okay. So how we detect using transit light? This is due to wind 20. Suppose a planet is rotating around its host star. If we observe from a face-on view, like the star is here, planet rotates like this, then only the transit light curve method can be used. If it rotates like this, you cannot detect. Why? Because if we plot flux versus time, then what happened? When the planet just comes in front of the star with respect to the observer, you can see a dip in the flux. Why? Because the light is blocked. Again, when the planet goes behind the star, you can see a smaller dip. Why is it? Because before going behind the star, the planet reflects as well as emits its own light, and when it just goes behind the star, there is a dip comes. But obviously, this dip is very much less than this one because planet's reflection and emission is very much less than the star. Okay. So
if it rotates in this direction, then also sometimes it will go up the star, bottom of the star. Sometimes it will be on face on. So there also you should be able to see the dip.
yeah, actually, most of the cases between face on or edge on, there are many different positions possible, right? Because it can rotate like this. These are points.
Yeah.
Except that there are 45, 135-degree angles. So the amount of this transit points will reduce.
So amplitude will not be that much low.
Exactly.
But if it is exactly at zero, perpendicular to this plan, then there is possibility that it can.
Yeah, obviously.
So as long as it blocks the light,
we can see. We can detect. Yeah. So this. No, we can. The probability decreases.
So light curve is constant light curve and then the deep. The deep will be less than.
Understood? So this is a of research is going on there. The probability. Sorry. Okay. So suppose star is like this and the planet is comes in front of the star. It goes from here to there. So at this point you will get a dip. Okay. Now if it goes like this, then depending on which position it crosses, the length of this curve will reduce. Understood? So if it,
is dependent upon the line. It's completely a function of the line of sight. The line of sight allows. In any angle you can alter because line of ecliptic plane of the planet.
Then we can.
The line of sight and the ecliptic plane. Based on that, it's cos theta.
Yeah. No, no. Complete your question.
So the probability of an exoplanet system that goes over that one pixel.
No. This is a very good question. But what you are discussed in direct imaging cases, where you can distinguish between planet and star. Here, what you can see, you can observe only the whatever flux that 1 pixel, but the intensity decreases due to the existence of the planet. So this decrease is in the flux intensity. That's why in y-axis this is flux. There is no point of getting star differently, planet differently. Is it convincing? Okay. So any questions? Okay. So depending on these two positions, like the transit position and the occultation position, remember what we can see at transit position, we can see only the night side, like dark side of the exoplanet, and on the occultation position, we can see only the day side. At exactly occultation position, actually you can't see anything, but there is some way how we can see the unseen things. I will come to it later. So depending on these two positions, sorry, there are three different spectra which can be observed as well as modeled. First one is the transmission spectra. This is observed during the transit, like primary transit point, this position. At that time, the starlight will come through the hot Jupiter atmosphere to us. That means it transmits to the atmosphere. So the name comes transmission spectra. Second one is the reflection spectra. This comes just before and after we getting the occultation point. At starlight will reflect it from the planetary surface and comes to us, and we get the reflected spectra. The same way, the exoplanet's own emission, which can, remember here, own emission means day side emission, not night side. Okay, own emission comes from at the occultation position. Okay, so my focus on the first topic is mainly on emission spectra. Raise one question: how can you distinguish between the reflection spectra and emission spectra at the first point? Okay, so there is a thumb rule that reflection spectra mostly comes in visible range, like for G-type stars, and emission spectra mostly comes for infrared range, like for Jupiter or hot Jupiter cases. But is there no no matching or no overlap? I'll come to it in my next project. Okay, so let's discuss emission spectra, two different things. So how to extract the spectra? See, there is a trick. when the planet just goes behind the star, before going behind the star, the light curve gives the star flux plus planetary flux. But when the planet just goes behind the star, we can see only the star flux. Now, if we subtract this part from this part, what we'll get? The planetary flux. So this is the way people extract the secondary eclipse or occultation position spectra. This is purely using photometry till now, but in JWST maybe they will use spectroscopy. Anyway, so this is the basic idea. Now something about emission spectra. For hot Jupiters, their temperature range is typically 1000 to 2000, 2500 Kelvin, and mostly their black body peak goes to infrared. The planetary flux ratio for modeling purpose is defined radius ratio square. Why? Because of the area what we see, the projected area, and the flux ratio, planetary flux and star flux. From this equation, we will enter in the theoretical view. Why? Because this radius is fixed, which can be observed radiuses, but the flux using the radiative transfer modeling theory.
Significant differences that we can observe some property with transmission spectrum and some with emission spectrum. Just both will kind of give an idea of their
Very good, very good. So idea is that, see, when we see the transmission spectra, whatever things we get is the upper atmospheric features first. Second one is the there is a permanent day side and permanent night side. Then where the day and night meets, that region is known as terminator region. So transmission spectra mainly consist of the information of the terminator regions. Okay, some people study habitability in this terminator region. So whatever properties we get from transmission spectra is the upper atmospheric region property, night side of this atmosphere. But emission and reflection spectra, we get the day side informations. So they are like complementary to each other. And finally, reflection and transmission both region, how much optical depth the starlight can penetrate. But only this emission spectra consist of the deep down properties goes from inside the planet. Like I think this is sun, like how much light comes from which. Although I'm not master in that, but still for an analogy. Okay. So okay. So next is how to model the planetary flux. So this is known as approximation for radiative transfer modeling. What does it say? See, for Earth's atmosphere, there are atmospheric curvatures, correct? But in modeling of exoplanetary atmosphere, we assume that there is no curvature in the planetary atmosphere. They are almost straight line or parallel to each other. What is the benefit of it? The benefit is that wherever the light goes, this is the light's going radiation's direction, that is ds vector. We can take a projection of this ds vector along its area vector. Sorry. So that whatever we do, we can calculate it in scalar radiative transfer equation. So it becomes very much easier than modeling a 3. Okay. So this is known as plane parallel approximation. This mu consists of cos theta, that is the direction cosine of the radiation going, and this equation is the general radiation where I represents the specific intensity which does not vary with distance. Xi source function which varies depending on our modeling technique. So and d tau is the optical depth, how much the light can penetrate. Okay. So this Xi is the most important part of our work or any radiative transfer solutions. I will come to it later. So this is the first approximation. Okay, so these are our basic assumptions and approximation for the whole work. First one is plane parallel approximation, which says there is no sphericity in layers. Eddington approximation, it gives a closure relation between all the moments of. Third one is the local thermodynamics condition, I think you people know that it ensures that the source function is equal locally, not globally. Next is hydrostatic equilibrium condition. That is, the pressure gradient is balanced by the gravitational force, gravitational acceleration. Next is radiative equilibrium condition. Some kind of uh, energy conservation. That is, from any layer, whatever radiation comes, that much radiation will go. Nothing is generated, none is absorbed. If absorbed, then it will be emit in some other way, but no energy is lost, no energy is gained. So that's it. These are all our basics which we will use for our further studies. Okay. So let's discuss about our first one. So what does it mean? Suppose we have some spectra of some particular hot Jupiters. Just by observing as well as modeling those emission spectra, can we say atmospheric flow in that hot Jupiter or not? Is there any possible way? Yeah, there is some possible ways. So the basic idea I want is very involved calculations. I will know not getting into that. Just take the basic idea. See, if we observe the day side atmosphere, now the day side atmospheric temperature is very much higher than night side. So there is a temperature gradient. Now what ideal gas law says? If there is temperature gradient, we will get pressure gradient. If there is pressure gradient, then obviously some atmosphere will flow from day to night, and this day to night circulation will reduce the heat and increase the heat on the night side. If it happens, then higher the atmospheric circulation, more heat will transfer from day to night side. Okay. If it happens, more the heat transfer from day to night side, less amount of heat will emit through the day side to emission spectrum. So basically, more the heat circulation, less magnitude of emission will come to. So this is the basic idea. The methodology radiative transfer is to establish a working relation between them. And for numerical simulation, we use discrete space theory formalism. I think one modified part of discrete space theory is known as Pali method, which is used by solar physicists in polarization studies. Okay, anyway. So this is the first time we use discrete space theory method for planetary atmosphere modeling. So this here the total secondary eclipse flux known as F full obviously consists of two particular parts. First one includes the internal flux of the planet, and the second one includes the radiation comes from its host star. The radiation comes from its host star can be represented by EQ0. What does it mean? Equilibrium flux at zero albedo. Zero albedo means no reflection. Okay. So this is fixed for a particular host star and at a particular distance from the star planet. F internal is also fixed for a particular planet. So if we fix the whole system and composition which ensures the AB, the bond albedo, then the parameters which can vary are the F effective and small f. Now what F effective represents? It represents how much heat is absorbed in which atmospheric layers. If it varies, then the F effective will also vary in terms of gamma. And the second parameter is the small f, which is our interest. Heat redistribution parameter. It is defined as how much heat is falling on the exoplanetary atmosphere divided by how much heat is redistributed. So I will discuss one by one. So in this equation, we have to model the final flux where everything else is fixed except F effective and small f. So let's attack the F effective term. So this is F effective variation with respect to gamma. If we vary the atmospheric absorption at different layers from 10 to the power minus 4 to 10 to the power 4, the F effective is this much. So the ratio becomes 10 to the power minus 5. So in our study, this value is very much less, and we assume, not exactly, but we assume that F effective is almost constant in all of our calculations. Okay. So the remaining part is the small f part. To discuss about it, let's imagine that there is a star and some light falls on the planet. Now, if the planetary radius is Rp and the light comes as a collimated beam. This collimated beam approximation is known as isotropic approximation. Collimated beam, then it will come through a disk of radius rp. So the area of irradiation will be pi rp square. Now, if the heat will redistributed in all of the atmosphere, then how much area is covered by the redistribution? 4 pi rp square. Simple. So for full redistribution, the ratio will be pi rp square by 4 pi rp square. It comes 1/4. Second one is semi. It gives that if the heat will be redistributed only in the day side part, that is half hemisphere, then it will obviously be 2 pi rp square, it becomes half. And finally, for no redistribution case, f will become 2/3. It cannot be shown simply because it includes some inward calculations. So let's take my words for it. You can see difference for further in no redistribution case. Okay. Nothing is redistributed. Basically, there is no time for redistribution. Just fall and reflects back. Exactly. Okay.
No atoms,
Sorry.
but no redistribution.
No atmosphere is the ideal case. Like for rocky surfaces, there or the icy surfaces, the albedo is so high that but for hot Jupiter case, for some particular composition in atmosphere, there might be some situation where redistributing the radiation time scale is so short that it will just reflect. Understand?
You're saying that there is no, they say all of the flux has been absorbed and then redistributed.
No. See, I distinguish between reflection and emission part. So whenever you are discussing all these things, you are discussing about for a sun-like star or a Earth-like or Jupiter-like planet, you are discussing in infrared. So to reflected, it's invisible.
So when you're talking about no redistribution,
Hmm.
you effectively mean a stagnant atmosphere.
Kind of.
Accumulation time scale is very high.
Yeah.
And even then, there's like 2/3
Uh,
of the heat is redistributed, like one.
like there. And this is some kind of obvious. Today only I found some paper that they discuss that hot Jupiters, even though are gravitationally locked, they are running. We don't know yet. Anyway.
But still the flux which is coming out from the reflection,
Mhm.
that should be constant because the planet has evolved over so many millions of years. So
Yeah, definitely. But that's the case for reflection spectra. We are talking here about emission spectra. So difference. Anyway. Okay, so these are some results which we obtained. So to characterize one particular exoplanetary atmosphere, it is compulsory to find their temperature pressure profile and chemical composition. Now what is temperature pressure profile? Depending on height, the pressure always decreases. Whatever things is that in Earth or any hot Jupiter or any sub-Neptune planets. Now depending on that pressure change, that how the temperature changes. This is the idea of a temperature pressure profile. So whenever you say someone about some exoplanet, people immediately ask what is its temperature structure. Depending on that, otherwise they reject it. Okay, clear? So this is a very basic property of a temperature pressure profile. Basic property of atmosphere, and this temperature derived from the emission spectrum. Okay, now for three particular redistribution cases, I have simulated these temperature pressure profiles where you can see for full redistribution, this temperature pressure profile goes like this. Why? What is the difference between semi and no redistribution cases? The first important difference is there is a thermal inversion. What does it? The pressure decreases with the height, with the in the y. But in this thermal inversion region, when the pressure decreases, the temperature. So this is some kind of going opposite to ideal gas law. This is some kind of anomaly. That's why this known as thermal inversion region. The thermal inversion region is very much important thing in exoplanetary study, and it can happen in many different cases. Like for our case, depending on less amount of redistribution, there are thermal inversion. Where chemistry people said that due to different chemical compositions in here, the absorbent are at the upper atmosphere, and thus the temperature increases. Whatever is the things, people are more in those exoplanetary atmosphere where the thermal inversion happens. Remember, Earth atmosphere also has a thermal inversion due to titanium oxide and vanadium oxides. Okay, so we showed that for full redistribution case, no thermal inversion can be seen. For semi and no redistribution cases, there are a amount of thermal inversion. Also, to observe at a particular atmospheric layer or a particular pressure level, the temperature increases depending on the redistribution factor. So decreasing redistribution increase the temperature on a particular atmosphere. Is being calculated.
How the temperature
Like how I calculated. Okay, I discussed some basic assumptions, right, at the early stage. Using those, there are some numerical simulations, and this is like little involved, and I cannot tell it. We can discuss it. Okay, so once these temperature pressure profiles are calculated, relative way, that's much I can say, and we can get the emission spectra, which can be matched with the observed data. And here also you can see more amount of redistribution, less amount of flux will come, and less amount of redistribution, more amount of flux. Negative correlation basically. Okay, so this part is published recently, and here I took the general case where I remove the isotropic approximation case, that the flux from the hoster is not further coming in a collimated way. It can come from any other way. And in that case, f can vary from 0.1 to 0.9. And in this case also, you can see the same interpretation goes. Okay. So our models are verified with some benchmark models known as Petit-Red or Exotransmit, as well as it is verified with some detected planetary data points. So these are benchmark. You can see this paper for reference. And finally, we predict for a particular hot Jupiter planet how much heat redistribution is there. The planet's name is XO1b. This was first detected by Machalek et al. And he got the data using HST IRAC, and fortunately they got only 4 data points. And after 2009, there are no further observations of this particular exoplanets. So we are limited by that, but still we are little successful on this. We use our full redistribution, semi-redistribution, no redistribution models, and finally particular temperature pressure profile for which the emission spectra observed data. Okay, so this data, this matching tells us that for this particular hot Jupiter planet, there might be some huge amount of redistribution of. Yeah, this one. So in theoretical modeling, there nothing comes as noise. This comes due to different amount of atmospheric compositions, their abundances and all. So all of them are particular line. Okay, so how we get those chemical compositions? There is a particular observation done by Giovanna Tinetti in transmission spectroscopy, she retrieved many chemical compositions present in this particular hot Jupiter. We use those particular abundances and use this one. This region? Huh. This one? This one? Huh. This comes, I think, due to H2O molecule. I'm not quite sure. No, no, no. We all are waiting. That's why we all are waiting for JWST. All of these answers will come. Anyway, sorry, is a particular chance to verify, support our idea. When we are working on this, the same TNET used transmission spectroscopy and told that there might be some heat redistribution, but they cannot sure about it. So they finished their paper like that, spectra study. Otherwise, we can. That's why we did that. And okay. Yeah.
So you said that the chemical composition of the atmosphere
Hmm.
is observed.
No, retrieved.
Okay, retrieved. So that is still observation. And then you use that composition to run your model.
Yeah.
So what is your model adding to it? Why do you actually need to run the model if you're using the chemical composition?
Okay. Very good question. So for retrieving the chemical composition, the approach is like that way, that what sorry, amount of chemicals are there. How can we get from transmission spectra, like from upper atmospheric region, we can say this much abundances are there. So we interpolate or extrapolate, you can deep into it and assume that these chemical compositions are same. After doing that, we can get the temperature pressure profiles, because only with chemical compositions we cannot say anything. Excuse me. Yeah. And okay, so that, we add the structure of this particular exoplanets. It varies with the pressure. Okay, fine. So
Just when you use your model, is it a low resolution or high resolution?
this one is for low resolution. Huh. There. Okay. At this 10 to the power minus 3 range, the atmospheric so less, thickness means directly, density is so less that the heat changing, or the, how can I say, that the temperature change with pressure is very much less. The chemical composition and the irradiation comes from the, at that level, at that so much less density, is the redistribution is there or not does not matter. Suppose there is a very huge number of cricket balls. It goes from here, you can see the change. Now suppose cricket ball, it goes from here to there. You cannot even find is there, it goes there or not. Understood my point? Is like we cannot eventually tell the everything about that. These are limited by observations. Uh-huh. No, no, boundary.
If you are modeling it from 1200 to 2200, right? And that is near.
Okay, okay. No, 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 no. Sorry, my mistake. Our modeling is not bounded from 1200. We started from 500 Kelvin to 3000 Kelvin. Here I plotted this as so that this feature can be seen easily. If I plotted here 500 to 3000, you might see it. Okay, that's this is the plotting difference. Okay, so these are the takeaway points from here. Depending on the atmospheric heat temperature pressure profile, simply known as thermal inversion, as I showed. The more the atmospheric heat redistribution, less magnitude of the emissions. That's our basic idea. What we have verified. Finally, for hot Jupiter cases, we support one other scientist in his results that X1b has a very huge atmospheric heat redistribution. Okay, so here ends my first project. Now I will go to the next one. So any questions? Yeah.
Would you have to identify the features of any molecule? Any features for a particular molecule? Titanium oxide, titanium oxide.
Yeah, but vanadium oxide and titanium oxide is not available in.
What kind of molecules are you found?
Okay, here we N2 and CO. Okay. Okay. Anything else? Okay, so let's go to my next project, the modified theory of Chandrasekhar's diffuse reflection. So this is one project which I have developed in my PhD period with greatest struggle I have ever faced, because you will see that the whole project is in single author, and the theory which I proposed is still okay. So the basic question is that to model the hot planetary atmosphere, how can we start? At first of my slide of my talk, I quote one question that if there is reflection and emission comes simultaneously, how can. So this is the basic question why I started this project. Okay, so let me simplify it in this way. Suppose if I ask one child that how you find the moonlight, is it moon's own light or it's sun's light which comes from moon? What will be his or her answer? Is sunlight reflected from planet, okay, reflected from moon. But if suddenly two people that if I observe one hot Jupiter, how can we say comes from the star itself, not from the planet? Can we say? What will you say? Okay, so let's discuss first principle introduced by Feynman. It said the first principle is that you must not fool yourself. You are the easiest person to fool. So whatever we have done is assuming one particular thing, that emission and reflection is totally different. And my are we making ourselves fool? So this was the question where I started this project. So let's make it little easier. Suppose for a Earth Sun system, the temperature difference is so huge. For Sun, it is almost roughly 5,500 Kelvin. For Earth, it's almost 280 to 290 Kelvin. So if we plot the black body curves, we can simply find that for Sun it is 0.5 micron, and for Earth it is about 10 micron. Okay. This is in optical, this is in infrared. But what happened when we go for a exoplanetary atmosphere? There are some beautiful things, beautiful dinosaurs are there. Suppose there is an ultra hot Jupiter rotating orbiting around. Their temperature difference is roughly 100 to 500 Kelvin. Okay, if I took such system and plot the black body curves, you can see their black body peaks fall same point. Okay, also there is a between their black body peaks, like the magnitude. So what can we do there? For Earth Sun system, remember there is a Chandrasekhar's diffuse reflection theory. This theory is developed by Chandrasekhar in 1960. This Chandrasekhar, and this same thing we use for Earth system, planetary system, exoplanet system, everywhere. But for this ultra hot Jupiter M dwarf system, is available till now. Okay, so this was a very challenging and surprising thing that by 60 years there is nothing. So the basic idea to do that is modify the source function. Remember I introduced xi in radiative transfer. That transfer equation using the simultaneous scattering effect. The method I will use is invariance principle method, discovered by Soumya, one fellow from Russia, and it's applied in Chandrasekhar's diffuse reflection theory. This there is a very involved mathematical calculations. I will not. I will give you some brief idea of it. Suppose there are atmospheric layers in plane parallel approximation. Okay, when the starlight falls like this is the pi f region, then light will scatter from the atmosphere. One thousand or 10,000 pencil or flux lines, one of them does not directly goes to the next layer and then starts scattering. Is the flux coming from the star. Okay. Pi shows the uh, azimuthal or azimuthal thing, I think. Anyway, so this term known as the reduced incident flux. This is same as the skin effect in the electronics, the electron skin effect. So simple, light falls, scatters, transmits, again scatters. What we add? We add one thermal emission each and every atmospheric layers. Okay. So this says that scattering and thermal emission, if happens simultaneously, happen to the observed flux, and we have to model it. That's the main challenge. This is a simple idea to how to model the exoplanetary atmosphere. These are the atmospheric layers. If the light falls, then it starts scattering, then again goes. See, there is of this light is greater than there and there. Why? Because after scattering and absorption, the magnitude of the light, and after certain depth, it is absorbed. What we have done is we add one black body emission effect, and obviously it is isotropic emission. Okay. So what is gives to go details into it, we introduce scattering function. This function S directly relates the final observed flux with the incident flux F. You can see that there is a proportional relation with I and F, and this proportionality constant roughly you can represent it with this scattering function S. Okay. Now to do that, we need to use there is some definition, but let me tell you in some analogy. Infinite number of glass slabs, and you are in front of one glass slab and see your face. Now if suddenly you remove one of the slabs of you, is it change anything? Because the next part is at so whatever the from that glass slabs will remain the same in that case of infinite glass slabs. Same thing goes for atmospheric layers, and it is known as invariance principle by which says that the reflection and transmission remain invariant while we add or subtract any atmospheric layers.
This is without the source function.
Which one?
This invariance principle is applied without before we put in the source function.
No. This does not depend on source functions at all.
Original Chandrasekhar. This is scattering and transmission.
But this gives a particular condition on our study. This demands a translational invariance. Yes.
Because if there is a temperature inversion in the atmosphere,
Mm-hmm.
then the black body corresponding to the peak temperature of the black body will change accordingly.
Exactly.
So if you assume this,
Mhm.
then you won't have any invariance.
Brilliant. That's why I told you that there is needs a translational invariance. It says that each and every glass slabs or atmospheric layers are in perfect homogeneity. There is no temperature difference, nothing. So it says that there must be a vertical isothermal temperature pressure profile. It means with temperature. For that particular limitation only, we can use our theory. Okay, till now I will remove that thing out as well. Okay, so be with me. So using all these things, sorry, what we can found is the final from the exoplanetary atmosphere. It consists of particularly two different terms. First term includes this mu and mu zero are direction properties. Okay, the first term includes the black body emission B from a particular temperature. Which temperature? The same temperature of each atmospheric layers, because it's isothermal fluid. The second one consists of the falls from the star to planet, and omega zero. This is known as the single scatter. What does it represent? The first term represents the effect due to emission from planetary atmosphere. The second term represents effects due to planetary reflection or scattering. Of this emission, you will perfectly get the reflection spectra. If you switch off the reflection part, you will perfectly get the emission spectra. And most when you have to model reflection and emission, that is, if suddenly one day moon starts emitting itself, then if you have to model the moon's emission spectra, you need to use both the effects. So that's the point why for hot Jupiter this theory is important. Okay, so thermal emission and scattering both comes in a particular level. All are done in a particular frequency. So this is the pictorial view. Okay, one more important thing is this M function. This M function is which is dependent, which is involved property of this final radiation coming to us, and this M function holds non-linear equation. It needs very much calculations, which I have not successful to done yet to get the value. But the most important point, direction. No optical depth, no chemical composition, no temperature profile, only a property of direction. Okay, so I'll give you one idea of this thermal emission case. Suppose along plus mu phi direction, here you sits. Now for a particular atmospheric layer, thermal emission directly far from the star's reflection from the planetary atmosphere will, as well as thermal emission will come to you. But at the beginning, you cannot differentiate between them. What you can see is the total effect in terms of M function. This M function represents the radiation you observed by the radiation from star. So once you get the ratio and you somehow estimate the star's own radiation, then it is just a matter of calculation to get the planetary flux comes. Then from the modeling and observation, you can find how much is due to reflection, how much is due to star's emission. Sorry, planet's emission. Okay, anyway. So till now, it is known as the semi-infinite atmosphere case, as I mentioned here, that the glass slabs are finite in one side and infinite in other side. The atmosphere is finite in both the sides. So what we can do is we need to introduce finite atmosphere case. In that case, we have, maybe you noted in the previous case, scattering function depends only on mu phi and only mu and mu phi and mu. But now transmission function also depends on this optical depth. Now how it tackles the problem to reduce temperature pressure profile condition. Imagine the same glass slabs you have. Now these glass slabs are not more homogeneous, they are inhomogeneous. Now you have finite number of glass slabs. Now Ambarzoomian said, suppose you remove one glass slab from here and put the same glass slab here, total effect of transmission and scattering remain invariant. So this, huh? What it mean? Suppose you have a finite number of glass slabs with different atmosphere or pressures. They are in infinity. Now, if we remove one glass slab from that side, glass slab in any other point like this, exactly, exactly. Huh. Huh. They are perfectly inhomogeneous. But the thing is that when you observe the transmission effect as a whole. Okay, so this principle ensures, you can read about it. This is very interesting. The effect, obviously, this is doubtful. Put it somewhere else, but still it shows the same effect of scattering and transmission, and it is verified. Okay, mathematically. So this is the finite atmosphere principle from Ambarzumian, which is mostly extended by the Nobel laureate Chandrasekhar, and this removes the isothermal temperature pressure profile condition. Okay, so this goes like this. There, the atmospheric layers further gets complicated. Some light gets scattered, some light gets transmitted directly, then scattered, some light. Many things happens. So this goes iteratively, and we cannot do analytical calculations. We have to shift. But for that, we need a vector equation. This is the final results from my paper on 2022. Mu plus here I introduced two functions, v mu and w mu, the scattered flux as well as the transmitted, and these are similar with Chandrasekhar's x function and y functions. So here goes a story. So this is related with my PhD. So this work was very much close to my heart, but this work in ABJ, then in a first review it was rejected. So reviewer gives the comment, there is a critical problem in this problem, and the author should read Rebecca Lightman's book to understand the idea. What I have to do? I have no other options. I reply to the editor of ABJ, writing that these are not the standard of ABJ. Please change the referee. And the editor replied me, please your paper again and we will judge. And after submitting this paper, it was accepted in a single review. Okay, so the point is that what the results interpret is very much unbelievable. Like this is not that much acceptable at the first part, because just by observing an exoplanet, you cannot clearly say that okay, this is star's emission, this is planet's emission. You cannot distinguish by it, and still this theory is in its infancy, and only two papers are on it. So it needs much more calculations and ideas, which I also need. I also don't know how to progress further. So anyway, the idea is that when the star is in front of a planetary atmosphere, then if the scattering only happens there, two famous functions, x and y function, discovered by Chandrasekhar, and this theoretical idea was given by Van de Hulst. It says, suppose observer is here, that is observer looks at the reflection and emission spectroscopy, then what he will observe? Only the x function, nothing else. And when the observer looks from a transmission spectroscopical view, they will observe only the y function, nothing else. But this is the case for only scattering. What we have done is we add simply a thermal emission part, and the for the scattering function as well as transmission function. Okay, and we observed only v function and w function. Remember, this v function will reduce to the m function which I introduced earlier, go from finite to semi-infinite atmospheres. Okay, So finally, there is a beautiful rules of transformation. It says, suppose here is a star and a planet rotates. Now, I am analogically telling, if the planet is there, you can see the transmission spectra of it, right? I can see the reflection spectra of it. If we both change the positions, then the total property of observation, the final observation, the complementary parts which we added, that cannot change. Understood? Like if you see the transmitted part, if I see the reflected part, then this W and V functions, they are interchangeable if the observers changes their positions. And this can be mathematically connected by this simple exponential law. Okay, at first it is very much like surprising, but it happens. No, suppose light comes from here, reflects from there and goes to him. If we change the source from here to there and sit him here, then the same light will reflect from here and goes to them. This is the reciprocity principle of Helmholtz, goes from one position to another. So this holds still here. Yeah.
So we are connecting the scattering and the transmission.
Yeah.
Generally, when that point was to differentiate between which one is the scattering
Hmm.
or the transmission. So, well, are you considering the atmosphere layers,
Mhm.
homogeneous over the entire planet?
No.
I understand when you're talking about the transmission spectra in particular, we're talking about those terminators of the densities.
Mm. Mm.
When you're looking at novelty.
Mm.
So when you're using the same theory for both the spectra and mixing them together, then aren't you just, isn't this assumption inherent or is there some other way to yes, if you're considering is homogeneous over
Something like if you think correctly, then it has to happen now. Suppose this is like inherent assumption of ours that we starts from here, so that due to light's inherent property, these things should be symmetrical. Understood my point?
what if you consider like at the very beginning you're talking about gravitation in of planets and you're considering if for a planet there is no redistribution, then the atmosphere is stagnant.
Okay.
But if there is very good redistribution, I can see that happening. That all that the source function, transmission functions are same. But if there is bad redistribution and it's stagnant, then it might be the case. I'm not sure. But it might be the case that in different parts of the planet, say in a part where the sunlight is there, and it's very strong. It's not much bigger. There might be slightly different composition and slightly different transmission functions as opposed to a twilight, so not the night.
Yeah, obviously. But this thing, what you said is due to this temperature, the things get changed chemically. Okay. Now, whenever we observe or talk about or modeling something, we are still in equilibrium chemistry situation, where for a long range of time, the chemical is the same. In that case, okay. So the takeaway points of the second project is that for Earth-like exoplanets, the diffuse scattering theory can be used, as I showed in early, or till now what people use. But for highly emitting exoplanetary atmospheres such as hot Jupiters, one should take care of the emission effect as well as scattering. That's why we need to consider both the effects together. Next is for exoplanetary atmosphere, it resembles finite atmosphere as it starts from its exosphere, the uppermost atmospheric layer, to the core, if there is any core, and from zero optical depth to a finite optical depth. Hence, our results what we obtained can be used in exoplanetary atmosphere rough. But here is a catch, like we need to develop this further to directly use them for numerical simulations, code development. What I have shown is for two particular atmospheric layers. If we go further, we need iterative processes, further things like chemical composition changes, non-linear, non-equilibrium chemistry things, non-linear temperature pressure profiles, all those things. But by that, we can at least say that so this is the final conclusion what I have discussed already. So we can at least say for Earth Sun system this theory is okay till now, but for ultra hot Jupiter M-dot star systems where the heating emission and scattering both comes in an equal footing, then we need to modify the theory of diffuse reflection, and we have to use the theory what I have discussed. So these all are my references, and finally, to develop this study further, I need theoretical, analytical, numerical, observational, and chemical, compositional, many things which need some collaboration because I am not expert in all those things. Maybe I am expert in all this theoretical part. Anyway, so I need some collaborations. I started something also. So if any of you get little bit of interest or any questions further, you can directly contact or shoot me a mail in this contact details, and I will be happy to discuss about it, talk about it, and if possible, work. Thank you. So any further questions?
We are interrupted so many times. I don't think they have any questions.
Thank you.
Then no further questions.
Okay. Thank you again.
Contact you immediately if they have any questions.
Yeah, definitely.
So we have tea for everyone in the corridor. Please